Okay, you've had a minute here. Remember, if f is differentiable at a point, it's got to be continuous. So, is this continuous at x equals 2?
What? No.
Oh, wait, that's derivative.
Oh, that's the derivative. See that? That's f prime. That was mean, huh? Okay. That's f prime. So f of x is going to be x and 3x squared over 2 plus c and plus c, right? Now it says here that f of 1 is 3, so I'll be able to tell what c is, right?
Can you do it for the second part though? Because it's not in the domain.
Well, c would need to be the same thing, since they're the same function. Okay? So that part, we've got 2, x is between 2 and 5. All right, so what are we going to use? The f of 1 is 3. We're going to use that in the first piece, right?
Yes.
So if when x is 1, the function equals 3, what does c have to equal? 2. Okay, 1 plus 2 is 3. All right, so I can get rid of that. Whoop, it won't let me erase. So I now know that my actual function f of x is x plus 2, and that's going to have to be 3x squared over 2 plus 2. Okay, and here it's when x is between 0 and 2, and here it's when it's between 2 and 5. Okay, so there's the function that we're looking for. So now let's ask the question, is it continuous at x equals 2?
No.
Well, that means both pieces would have to equal the same thing if x were to equal 2, right? Basically, we're taking the limit as x approaches 2 from the left of x plus 2, which is 4, all right? And if we plug in 2 here, we get 4 times 3 is 12 over 2 is 6 plus 2 is 8. So, is it differentiable? No, it's not even continuous there. Okay? Because 4 doesn't equal 8. In case you were wondering. All right? So, it's not continuous. Now, if it were continuous, we would then also need to look at the derivative. We would need to say, is it smooth? In other words, you would need to take the derivative of both pieces and plug in 2 and see if you got the same slope, because that's what will help us avoid some kind of a sharp turn like that. Okay? If they both have the same slope, then one will come in and the other one will pick up at exactly the same slope. And that's what will make it smooth, or no pointy edges, and therefore differentiable. Now, we don't even have to test that here because it wasn't even continuous, so we can just be done. All right?
So what is it referring to when it says f is continuous? Should it be f prime is continuous?
Wait, that's a good question. You know what? Maybe that's implying that the C's don't have to be the same.
Okay.
That must be what that is.
Yeah, it is.
So this C is 2, but this C doesn't have to be 2. That's a good point there. I missed that. So let's actually revisit here and think about what that would mean. Okay, so that's 2 plus 2 is 4, so this thing has to equal 4. And when I plug in 2, in order for it to be continuous, right? So 2 squared is 4 over 2 is 2 times 3 is 6. If I need it to equal 4, that means C must equal a minus 2, okay? So we've got actually this minus 2. That would force it to be continuous. Okay, I'm glad you caught that, thank you.
So C can be
Alright, so now let's actually do tests to see if it's smooth, okay? So the derivative of x plus 2 is just 1. So when x equals 2, the slope is 1. Alright? The derivative of 3x squared over 2 minus 2 is just a 3x. Okay? So when x equals 2, that one has a slope of 6. Okay? I took the derivative of 3x squared over 2 minus 2.
Wait, but why we need to do this? We will
就是
make
从右移向2，它是等于就是
Well, the reason is because if it's going to be smooth, which is what's required for it to be differentiable, then the slope here has to be, the slope from one side has to equal the slope from the other side. So that when you hit that point, here's a slope of 1, well the other side has a slope of 6, so that's going to create a point. So it is not smooth, so it is not differentiable.
3种这种就是不可能的，就是不能 differentiate 的这种情况，就是
Okay?
导数为
So there's a little bit of practice there for us, needing to use a little bit of integration as well. All right. So now let's do a little bit of review from our pre-calculus days of sigma notation. This is something we worked with some in pre-calculus. Not a ton, but I did want to just review it quickly here, so that you guys have seen a little bit of it. All right. So when we're using sigma notation, remember we're finding a sum. All right. That's why they use the letter sigma, because it's the Greek letter for S, and it's sum. All right. So when we have the sum from I equals 0 to 5 of something like I plus 1, we're simply going to take 0 and plug it in for the I, and then we take a 1 and plug it in for the I, and then a 2 and plug it in for the I, and then 3, and then 4, and when do I stop? When I get to 5, because 5 was that top number. Then I take each of those and I add them all up. Okay? So I have a 5, a 5, a 5, and a 6. So 21 is what that would add up to. Okay? That's pretty simple. Now, we also have here another one, j equals 3 to 7 of j squared. Now, this is one where we did have a formula that we looked at. We actually proved this using math induction back in pre-calc honors. We used the math induction and proved the sum of the squares. All right. However, that one gave us the sum of the squares from 1 up to a number. Here we're just doing 3 to 7. Okay. So you have a couple options of how you could do it. We could find the sum from 1 to 7 using the formula, and then subtract the 1 with 1 and 2 in it. Okay. Or since there's only 4 numbers here, we could go ahead and just add them up. 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Okay, it's not too much work there. So 49 and 36 would be 70, 85. Plus 25 is going to be 110. plus another 25 is 135. So that'll total up to 135. Okay? Okay? Then we have this thing here. C is a constant. All right? How did we handle it when we had the sum of a constant? Yeah, it's just 4c, because when k is 1, this equals c, and when k is 2, it equals c, and when it's 3, it equals c, and when k is 4, it equals c. So that's just 4 c's. All right, so if you have a constant, it's really just count up how many terms you want, and it's going to be that times the constant. Okay? All right, now the last two here actually use some properties that we learned before that I want to remind us of. The first one here is, you'll notice here we're going from k equals 1 to n. We don't know exactly how far we're going. All right? However, because k is the counter here, it's the thing that's going up, that 1 over n is just a constant. So that's going to appear in every single one of those as I'm adding it up. Or I could actually pull that constant outside the sum and go from k equals 1 to n of just the k squared plus 1. Okay? Does that make sense? Now, at this point, another thing that I could do is I could actually split up that sum, okay? The sum of a sum, I can split it into two different sums. All right, so I'm going to put some brackets here. I have the sum from k equals 1 to n of k squared plus the sum from k equals 1 to n of 1. Okay? So that's just a plus n on the end. So I have 1 over n times, and that's going to be a plus n at the end. We had the formula for the squares. It's n times n plus 1 times 2n plus 1 all over 6. It's okay if you don't remember that off the top of your head. But notice now when I multiply in the 1 over n, guys, when I multiply in the 1 over n, it's going to actually cancel out the n on the first part. So it'll just be n plus 1 times 2n plus 1 over 6, and then it'll cancel out that n as well, so it'll be a plus 1 on the end. Alright? So now, whatever n is, we just plug in the n and we can figure out what the sum equals. Okay? So that's a little bit of review, what we're going to be using here in the near future.